Right, what I got here today is this lamp. It's an LED lamp. What they do is they take this, it starts off flat, and they roll it up, and then they push it down the tubes like that. And that becomes a LED version of the compact fluorescent lamps that we had years ago. This it lasts. So that's been cemented in over there. So this stopped working, and I had a look, and there's little black bits in the LEDs. So it's an LED failure. There you can especially see it. They got cooked. So that's what goes wrong with these things. Anyhow, the little driver circuit's what I want to talk about today. It is a constant current buck regulator. And on the board, what you have is the regulator IC. There's a 3 ohm current measurement resistor. And then over there, there's a Schottky diode. On my bad printout, because me and printers don't seem to get things done. Right. Anyhow, what I've done is I've made a drawing. Now that 75 CYL 80260 I can't find on the internet, but I reverse engineered it. It's a very simple thing. So over here, I would say that that inductor is probably around 2 millihenry in size. So what you've got is bridge rectifier over here, standard bridge, 5.6 microfarad 500 volt cap, smoothing cap, that's DC. And then the other components, there's your resistor over there. Hidden over there is a Schottky diode down there, and then the IC itself, and the inductor. Try to keep the light out of your eyes. So what's happening here, my scope probe's falling off, but that's okay. DC bus charges up, powers up the chip. What the chip does is it switches on, current flows through the inductor and through this 3.3 ohm resistor. When it fires it up, and when the transistor in here turns off, the current flow reverses. Current flows through the LED and through here, through that resistor, back to negative. So I've got a single LED powered up off it over here. So it's a 12 volt LED. And what I'm doing is I'm powering it up off a power supply of 60 volts. Now this is rated for 220, 230 volt mains operation. So I've got it at 30 volts at the moment. So as I turn it up, you can see the frequency increasing over there. So that is with respect from the positive rail over there to there over the LED. Right. Let's add a measurement. Frequency. Yeah, 22 kilohertz. That's what I was measuring. So as we drop it down to 5 kilohertz. So there you can see the transistor turning on, and there you can see the inductor discharging again. Now if I disconnect that, and we have a look at this point over here, that point over there. Now we should see it switching. Bring that up a little bit. So take it up to 60 volts, and then move that up further so that we can see. Increase the time base. You can see that the pulses have become very narrow. Now what's happened is the current on the power supply has come down to 20 milliamps. So as I bring the voltage down, the pulses get wider to keep the current through my LED over here constant. Because it's constant power, I'm now down at 30 volts. I'm now at 4 milliamps on the power supply, because we're still delivering the same amount of power to the LED over here. So as I bring it all the way down, you can see those on pulses becoming quite long. So that's actually at 20 volts now, so we're now at 120 milliamps. So the on time has become quite long. The regulator chip is actually not enjoying that too much. Frequency at the moment is 16 kilohertz. 60 volts is 22 kilohertz. That's kind of the point where you got to mind your fingies around this stuff, because you can get zapped. Also, the benefit of having a 60 volt power supply is one gets to do these sort of experiments. So that is what the PWM looks like. Coming out of this thing. That's what it looks like going to the LED over there. So you can see as I change the voltage, the LED current doesn't change. And of course this voltage across it is staying constant. You'd see that change if there's a change in current as well. I don't have something handy to measure this current at the moment, but I think that's a sub-quest on its own. We're not going to bother with that today. We are talking about this driver circuit, how the PWM works. So when one of these LED lamps fails, which was this, one can actually harvest that out of it, and you can use it to run a lower voltage LED straight off the mains, such as I'm doing with this 12 volt one over here. It'll happily do it for you. And if you want to adjust the intensity on this on the output, because we're basically delivering 100 milliamps to this LED, that's what it draws off 12 volts. You just change that burn resistor over here, that value here. If you increase that value, you reduce the current on the output. You can adjust your current to your LEDs to suit your application. So that's a useful little thing to keep if one wants an LED driver for another project. If I wanted to drive little 10 milliamp LEDs with it, to modify that resistor, and that's nice and small, it'll fit into a little enclosure if I wanted to make a little display or something, such as an item like this is display for cars. That would be perfect for this, because I could drive these LEDs in series I could hide that somewhere because it's small. I could easily make a box on the back for it, another cover that fits over here, and it just takes mains in for the little display. So that's the story. So now I know what these look like inside, and we know why they fail, because those LEDs go bad. Let's see, you can see what I'm doing there, like so. This starts off its life flat like that. You can see the traces on it over there. 1, 2, 3, 4, 5, 6 times 6 is 36 times about 3 volts, it's 180 volts. So these are probably all in series, so when the first one goes out, then the whole lot dies, stops working. And looking at the traces, yeah, I can see that it loops around like that. They must have been pushing these quite hard. The base of this says 7 watts, 300k, a warm LED. Might have been wrong about that voltage, because if this will run down to 85 volts AC, then they were probably putting these 2 sets in parallel, which would put you at 90 volts, which 85 volts after AC and give you enough to power that. So that sounds about right. So that how that lives off anything from 110 to 265. This is basic. There's space there for a class Y capacitor. There's no input inductor or filtering or any of that stuff on it. So this is a pretty sort of budget friendly light, if you were. But you know, for something which requires a little constant current source, and you're left with them because these don't last, they're useful. Not the best, not terrible, but it'll get the job done. It's also non-isolated, so you've got to bear that in mind. Everything lives at mains voltage. So that over there, yeah, that is it. I think there's nothing left to talk about here. I had to reverse engineer it because I can't find that part number, but it's not complicated, and there may even be errors here, but that's pretty much what it's doing. Right, gonna wrap it up at that. That is it. I'm done with this one. Take my probe off here. What were we seeing? Bump the microphone. So that was positive. Yeah, that's a little bit of voltage across the resistor there. That's the other side of it, which is at negative. can't get it to make contact there. And there's what's happening across the diode. That's how then, so that's that pin over there. Yeah. Got this scope propped up so you guys can see it. One last look. That's it over there. Pulse width modulation. How it works. Now buck regulator works. Anyhow, you must be tired of me by now. Let's go. Thanks very much for being here today, ladies and gentlemen. Hope you enjoyed this quick little talk. It was an interesting little one. Take care. I'll see you next time for more interesting stuff. Cheers.